brakes are applied on a moving train, brake shoes are forced against the wheels to slow them down. This causes the shoes and wheels to heat up, which can lead to serious failures or accidents. A safer and more efficient system of braking is available on most of our road diesel locomotives. This system is called dynamic braking. The dynamic brake is an electrical braking arrangement that changes some of the power developed by the momentum and downhill force of a moving train into electrical power, which is then dissipated in the form of heat. Let's see how this is accomplished. The fact that a DC generator and a DC motor are constructed basically the same allows them to be changed from one to the other by merely changing a few connections. It takes power to turn a generator. This power can be taken from waterfalls, wind currents, a diesel engine, or even from the power in a moving train. The traction motor armatures on a diesel locomotive are geared to the axles. They rotate whenever the locomotive is moving. If we change the connections so that the motors function as generators, they will absorb some of the power from the moving train. This not only slows the train, but also creates a considerable amount of electricity that must be disposed of quickly. Since this electricity cannot be stored, it is converted into heat, similar to the way a toaster converts electricity into heat, by passing it through heavy resistors called grids. The grids are kept at a safe temperature by blowing the heat out to the atmosphere. On EMD units, a portion of the current is used to run fan motors. On GE, a large fan is driven from the engine crankshaft. The load ammeter indicates the dynamic brake current. Its use is similar to the brake cylinder gauge when using the independent brake. All of the retarding force, or braking, is concentrated on the locomotive units, similar to an independent brake application. The amount of dynamic brake force is influenced by two things. One is the amount of current flowing in the motor fields or stationary coils. This field current is controlled by the position of the dynamic brake handle. The other is the speed at which the motor armatures rotate, which is related to the train speed. Brake force is expressed in pounds. Each motor is capable of producing 10,000 pounds or more of brake force. The most effective dynamic brake force is attained at a speed between 18 and 26 miles per hour, depending on the gear ratio on the unit. Since most units will develop maximum braking at about 23 miles per hour, we will use this speed throughout the program to indicate the most effective braking speed. When the brake handle is fully applied, the brake force will increase as the train speed increases, up to 23 miles per hour. After that point, brake force will decrease as the train speed continues to increase. There are two systems of dynamic brake currently in use. One is called the taper system and is applied to EMD units. The other is called the flat system and is applied mostly to GE units. The taper and flat systems develop about the same brake force for a given handle position while the train speed is below 23 miles per hour. Here we see how the brake force is increased as the handle is moved out to the 8th position. But above 23 miles per hour, the two systems develop a different amount of brake force in all handle positions, except in full braking. This graph shows the difference between the two systems in the 5th notch. In other words, the difference in the two systems will be seen when train speed is over 23 miles per hour and the brake handle is in a position below number 8. With the EMD taper system, the brake force is determined by the position of the brake handle and the train speed. The brake force continues to increase as the train speed increases. In the reverse manner, the brake force will decrease as the train speed decreases. Consequently, the taper system tends to maintain a particular speed for each brake handle position. As the train speed increases, the taper system will reach maximum brake current of 700 amperes in successively lower handle positions. Once the units have reached maximum brake current, further advance of the brake handle will have no effect. However, with the GE flat system, the brake handle position represents a certain amount of grid current when the speed is above 23 miles per hour. This allows the brake force to decrease as train speed increases, an effect opposite to the taper system. The brake force developed by the flat system is different for each handle position, regardless of speed. Thus, the engineer can change the brake force at any speed with each change in handle position. Maximum brake current of 700 amperes will not be reached with the flat system until the brake handle is placed in number 8 position. When the two systems are mixed in a consist, units with the taper system will have a higher brake force than those with flat if the speed is above 23 and the handle is below number 8. The higher the train speed, the greater will be the difference. When running a train from a unit equipped with the EMD taper system, even though the leading unit is at maximum braking, you must advance the brake handle to increase dynamic braking on trailing units that have the GE flat system. The brake force of these standard systems, either taper or flat, will decrease gradually as the train speed reduces below 23 miles per hour. A feature called extended range may be added to either of the standard dynamic brake systems. This feature will continue to develop the maximum brake force from 23 miles per hour down to approximately 6. This makes a significant difference in the brake force between extended range units and standard dynamic brake units. Here the difference becomes greater as the speed is reduced below 23 miles per hour. Engineers must always be aware of the characteristics of the dynamic brake on units in their consist and of the effect the train speed will have on them. Dynamic brakes are controlled from the leading unit of a locomotive consist in the same way that power is controlled. The brake handle position determines the brake force request. The controls are train-lined through the consist so that all equipped units will respond, even if non-equipped units are coupled in between. Units that are isolated will not respond to dynamic brake control, nor will any units that do not take power for other reasons. On the latest type control stands, a separate brake handle is provided above the throttle for control of the dynamic brakes. This handle is mechanically interlocked with the throttle so that the brake handle cannot be moved out of off position if the throttle is above idle. The brake handle is also interlocked with the reverser handle so that the reverser cannot be changed while the dynamic brake is applied. This type of brake handle has two detent positions, or notches, marked off and set up. Then an operating range of 1 through full 8, through which the handle moves freely without notching. The brake handle is moved from left to right to increase brake force. The positions are indicated either in a small window above the handle or on a plate beneath it. The handle grip is somewhat out of round, with the flattened surfaces vertical to distinguish it from the throttle handle. On older models, a selector lever is used to select either power or brake, and the throttle handle is used to control both modes. The dynamic brake current is shown on the load indicating ammeter. Later models are equipped with a zero center type meter. The meter needle swings to the right of zero to indicate power, and to the left of zero to indicate dynamic brake current. On older models, dynamic brake current is shown by the same needle movement as power. On these meters, a red triangle, or other symbol, will be seen near the 700 ampere location to indicate the maximum brake current allowed. All All units that are equipped with dynamic brakes have a device that automatically limits the grid current to the maximum permitted by equipment design, usually 700 amperes. This device is called the dynamic brake regulator. A brake warning light is installed on all equipped units to indicate excessive brake current. If the regulator is working properly, the brake warning light should seldom, if ever, come on, and then only momentarily. Equipment damage is possible if the brake warning light stays lit for more than 2 or 3 seconds. When the light comes on, brake handle movement must be stopped, and if the light does not go out, the brake current must be reduced. The brake warning light is train-lined so that warning is given in the lead unit when a trailing unit exceeds the maximum brake current. Therefore, action must be taken when the warning light comes on, regardless of the meter reading. All road units, whether equipped with dynamic brake or not, have a dynamic brake interlock. This device locks out locomotive brake cylinder pressure when the automatic brake and the dynamic brake are both in use. If the brake shoes are forced against the wheels while the dynamic brake is applied, the wheels may slide, causing flat spots. When using the automatic brake with the dynamic, depress the independent brake handle frequently to ensure that locomotive brakes do not apply. A dynamic cutoff switch is activated during emergency and penalty brake applications to nullify the dynamic brake. When the dynamic brake is nullified by this feature, the locomotive air brakes will apply. An independent pressure switch is used on units that have extended range dynamic brake. This switch is operated by locomotive brake cylinder pressure. It nullifies the extended range feature and returns the unit to the standard characteristics when the independent brake is applied to 15 pounds or more. When brake cylinder pressure is reduced below 10 pounds, the extended range feature is re-established. On some units, a dynamic brake cutout switch will be found on the engine control panel. Its purpose is to cut out the dynamic brake on that unit in event of dynamic brake failure or to limit the number of axles that are used for braking. A 10 ampere dynamic brake control circuit breaker located on the control stand must be in the on position in the leading cab in order to operate the dynamic brakes. If this breaker trips while the dynamic is applied, the dynamic brake will drop out instantly on all units in the consist. Immediate action must be taken to prevent a run out of slack. Another breaker that can affect the dynamic brake is the brake transfer control breaker. This breaker affects the changeover switches which set up power or braking. If the transfer control breaker trips, the unit will operate only in the mode that it's in at the time the trip occurs. In other words, if the breaker trips while in power, the unit will not change over to dynamic braking. A good understanding of the operation and features of the dynamic brake is essential for all engineers. This brake can be used very effectively to control train speed on descending grades or during slowdowns. It is more practical to use the dynamic for the necessary changes required to hold train speed steady, since the intensity can be changed rather quickly compared to the train air brakes. Remember, the dynamic brake produces heat at the brake grids, where it will do no harm, rather than at the brake shoes and wheels. It's a safe and efficient method of controlling train speed. Use it at every opportunity.